Hello everyone. Today we will study double integrals over general regions. Last class we studied double integral over rectangular region. Last class we studied double integral over rectangular regions. Today we will study double integral over general regions. First of all, let me show you two types of general regions. Let me first of all show you two types of general regions. Type 1. Type 1 general region looks like this. On the top and the bottom, the region is bounded by two curves. On the top and the bottom, the region is bounded by two curves called y equal to f of s1 y equal to f1 of x. The bottom curve called y equal to f2 of x. On the top and the bottom is bounded region. On the top and the bottom, they are bounded by two curves. On the left and right, they are bounded by, the region D is bounded by two vertical lines called S equal to A, S equal to B. That's type 1 region. On the top and the bottom, it's bounded by two curves. On the left side and right side, it's bounded by two vertical lines. That's called type 1 region. Type 2 region looks like this. On the left side and right side, it's bounded by two curves. Called x equal to g1 of y. The other one is s equal to g2 of y. On the left side and right side, it's bounded by two curves called s equal to g1 of y, s equal to g2 of y. On the top and the bottom, it's bounded by two horizontal lines. On the top and the bottom, it's bounded by two horizontal lines called y equal to c, y equal to d. On the left side and right side, it's bounded by two curves called s equal to g1 of y, s equal to g2 of y. On the top and the bottom, it's bounded by two horizontal lines, y equal to c and y equal to d. That's called type 2 region. And type 1 region and type 2 region in set Peter notation looks like this. Type 1 region D in set Peter notation looks like this. D is the set of Sy in R2. D is the set of all points Sy in R2 such that S is between A and B. Y is between f2 of x and f1 of x. f2 is smaller, we must write it on the left side. f1 is larger, put it on the right side. Type 2 region D looks like this. The set of Sy in R2 such that Y is between C and D and X is between G1 and G2. write left side first, then right side. Those are the type 1 and type 2 region in set builder notation. Next, I will show you how to find double intervals over type 1 region and type 2 region. Look at this example. Let D equal to Sy in R2 such that S is between A and B and Y is between f2 of x and f1 of x. Let D be a type 1 region. And assume f of Sy is continuous on D. Let me draw the picture again. On the top and the bottom, region D is bounded by y equal to f1 of x, y equal to f2 of x. On the left and right, it's bounded by two vertical lines. S equal to A and S equal to B. Let C be a constant such that y2 f2 of x is greater than C for all x between A, B. Let C be a constant such that f2 of x is greater than C. So f2 of x is above C. f2 of x is greater than C for all x between A, B. Then this is y equal to C. C is completely below f2 of x. Let D be a constant such that f1 of x is less or equal to D for all x belong to AB. So let D be a constant. Let D is greater than f1 of x. Then the constant y equal to D, the constant function y equal to D is completely above f1 of x because f1 of x is completely less than D for all x in this interval. Let R be the rectangular region let R be the rectangular region AB cross CD. Let R be the rectangular region AB cross CD, so this is R. The small region here is D. The larger region is R. Let R be the rectangular region AB cross CD. Next, let me define a new function G. Let G of Sy be defined as G of Sy equal to f of Sy if Sy belongs to D, and G of Sy equal to 0 if Sy doesn't belong to D. Next, I define a new function called G of Sy. G of Sy equal to f of Sy if Sy belongs to D, and G of Sy equal to 0 if G of Sy doesn't belong to D. Now, by this definition, we can see that for any region inside region D, G of Sy, G is the same as f. For any point inside this region D, G of Sy equal to f of Sy. And for all points outside region D, G of Sy is 0. Then, by this definition of function G, we can see that double integral of function G over region R must be the same as double integral of function G over region D. Remember, double integral represents volume between the surface and the xy plane. Double integral represents the volume under the between the surface and the xy plane. If G of Sy is 0 outside region D, then the surface G equal to G of Sy is G equal to 0. G equal to 0 is actually the xy plane. The volume between xy plane and xy plane is 0. So for all region outside D, the double integral of G of Sy is always 0. For all region outside D, the double integral G of Sy is always 0. Therefore, double integral of G of Sy over region R is the same as double integral of G of Sy over region D, because everything outside is 0. That's one thing. A second thing, by this definition, double integral G of Sy over region D double integral G of Sy over region D must be the same as double integral f of Sy over region D. Since on region D, in this region D, f and g is the same. They have exactly the same surface. G equal to f of Sy, the surface G equal to f of Sy is the same as the surface G equal to G of Sy. If these two surfaces is the same in this region D, then the volume below the surface must be the same. If the surface in region D is the same for both f and g, if the surface is the same in region D, then the volume below the surface must be the same. Therefore, in region D, double integral of g is the same as double integral of f. Combine these two statements together. We know that double integral of g of Sy double integral of function f of Sy over region D is the same as double integral of g of Sy over region R. By this definition, by these two statements, we can see that double integral of f on region D over region D is the same as double integral of g over region R. Then, for double integral For double integral of R, double integral of G over region R, by Fubini's theorem, it can be written as integral, since R is a rectangular region, by Fubini's theorem, double integral of G over region R can be written as integral x from A to B, y from C to D, g of sy dy dx. Let's look at the inner integral first. For all x between A and B, the integral y from C to D, g of sy dy can be rewrite as what? Look at the picture. For all x between A and B, say somewhere here, for all x between A and B, this integral from C to D, this integral represents integral from C to D. It can be rewrite as integral from C to f2 of x. This integral can be rewrite as y from C to f2 of x. Y from C to f2 of x. Plus y from f2 of x to f1 of x. Plus y from f1 of x to D. So, for all x between A and B, the integral y from C to D can be written as these three integrals: y from C to f2 of x, y from f2 of x to f1 of x, then y from f1 of x to D. That's integral y from C to D, y from C to D. Now, we know that g of sy is 0 outside region D. G of sy is 0 here and here. So for y between C and f2 of x, g of sy is 0. For y between f1 of x and D, g of sy is also 0. So we get 0 plus the last one is also 0. G of sy is 0 here, is 0 here. Then integral of 0 is 0. For any definite integral of 0 is 0. So integral from c to d g of sy dy equal to integral y from f2 of x to f1 of x g of sy dy. This is the inner integral. This is the inner integral. Plug back. So double integral g of sy over region R. Double integral g of sy over region R is this double integral x from A to B y from f2 of x to f1 of x g of sy dy dx. And also we know that double integral of g over region R is the same as double integral of f over region D. Therefore double integral f of sy over region D is this integral s from A to B y from the lower curve to upper curve y from lower curve to upper curve g of sy and g of sy in region D. G of sy is the same as f of sy. In region D, g of sy is the same as f of sy by its definition. In region D, g of sy is the same as f of sy. So in region D, g of sy is the same as f of sy. dy dx. Similarly, for type 2 region of D, region D, with D equal to sy in R2 such that x is between y is between C and D and x is between g1 of y and g2 of y. The double integral f of sy dA is y from C to D. X is between the left side curve and the right side curve. S is between the left side curve and right side curve. Left side comes first. G1 of y, G2 of y, f of sy dx dy. Since x stays inner, we must write dx first, dy. If we compare this formula with type 1 region, we can see that for type 1 region, we integrate from bottom to top. So we write the bottom and top as your inner bound. Run the bottom curve and the top curve as your inner bound. And since left bound and right bound they are constants, I write it as upper bound. Now for type 2 region, same thing. We integrate from left to right. So we write the left side function, right side function as your inner bound. Run the left side function and right side function as your inner bound. The outer bound must be constant, so outer bound is from C to D. Keep these two formula in mind. That's how we take double integral over general region D. Keep these two formulas in mind. If we integrate from bottom to top, write bottom and top curve as your inner bound, and the constant on the left side and right side is your outer bound. If we integrate from left to right, write left bound and right bound as your inner integral, as your inner bound, and write the top and the bottom, the constant as your outer bound. Next, let's look at some examples about double integrals. First integral, outer bound from 0 to 2, inner bound from 1 to x, 12sy dy dx. We keep outer bound the same. Solve the inner bound first. If we solve the inner bound, take antiderivative with respect to y. So we have 6xy squared. Evaluate from 1 to x. Then if I plug in x, I have 6x to the power 3. If I plug in 1, I have 6x dx. Then take antiderivative from this function. This is a single variable function. Take antiderivative with respect to x. I have 6x to the power 4 over 4 minus 3x squared. Evaluate from 0 to 2. If I plug in 2 to the power 4 is 16. 16 over 4 is 4. 6 times 4 is 24. If I plug in 2 here, 2 squared is 4. 4 times 3 is 12. 24 minus 12 is 12. Next, outer integral is from 1 to e. Inner integral is from 0 to 1 over y. E of sy. Evaluate e of sy dy dx. Sorry, dx dy. So we solve the inner integral first. First of all, keep an outer integral the same. Take antiderivative with respect to x. I have 1 over y e raised to xy. Evaluate from s equal to 0 to s equal to 1 over y dy. Keep outer bound the same. If I plug in 1 over y for x, I have 1 over y e raised to power 1. If I substitute 0 for x, I have 1 over y. E to the power 0 is 1 dy. Then this can be rewrite as 1 over y times e minus 1 dy. E minus 1 is a constant. I leave it the same. E minus 1 is constant, leave it the same. Take antiderivative for 1 over y. I have ln of y. So keep e minus 1 the same. Take antiderivative for 1 over y. I get ln of y. Evaluate from 1 to e. If I substitute e, ln of e is 1. If I substitute 1, ln of 1 is 0. So the final answer is e minus 1. Next example. Evaluate the double integral over region R. The function is 3 minus x minus y dA, where R is the region. R is the set of all sy in R2, such that s is between 0 and 1, and y is between 0 and x. First step, always draw region R first. First step, always draw region R first. Here, draw the dependent part first. Y depends on x here. X doesn't depend on y, but y depends on x. Draw the dependent part first. Y is between 0 and x. That means the region is between y equal to 0 and y equal to x. Y is between 0 and x means the region is between y equal to 0 and y equal to x. How is y equal to 0 looks like? Y equal to 0 is the x-axis. Y equal to x is this line. So this is y equal to 0. This is y equal to x. X is from 0 to 1. S 0 is here. S equal to 1. S equal to 1. That's a vertical line that going through 1. That's region R here. That's region R here. So in this region, we know the lower curve, we know the upper curve, we know the left bound, we know the right bound. So we integrate from bottom to top. The lower bound is y equal to 0. Upper bound is y equal to x. X is from 0 to 1. Then the function stays the same. 3 minus x minus y dy dx. Then we solve the inner integral first. Keep the outer the same. Solve the inner integral first. Take antiderivative with respect to y. So antiderivative of 3 is 3y. Since I treat s as constant, antiderivative of x is xy. Antiderivative of y is y squared over 2. Evaluate from y from 0 to x. Dx. Then we substitute x for y, and substitute 0 for y. If I substitute x for each y, I have 3x minus x squared minus x squared over 2. If I substitute 0, I get 0. Then simplify this expression. X is from 0 to 1. 3x minus 3 over 2 x squared, combine like terms. Then take antiderivative with respect to x. We have 3x squared over 2 minus 3x to the power 3 over 3x to the power 3 over 3 over 6. Evaluate from 0 to 1. If I substitute 1, I have 3 over 2 minus 3 over 6. 3 over 6 is 1 over 2. Answer is 1. Next example. Evaluate the double integral over region R, where the function is s plus y dA, where R is the set of sy in R2 such that S is between y over 2 and 3 and y is between 0 and 6. First of all, let's draw region R first. Here, x depends on y. Y doesn't depend on x. X depends on y. So draw the curve for x first. X between y over 2 and 3, that means left bound is x equal to y over 2. Left bound is s equal to y over 2. Right bound is s equal to 3. S equal to y over 2 is the same as saying y equal to 2x. Then draw the graph. Left bound is s equal to y over 2, which is the same as y equal to 2x. That's a straight line. Y-intercept is 0. Slope is 2. So left bound is s equal to y over 2. Right bound is s equal to 3. S equal to 3 is a vertical line passing through 3. S equal to 3 is vertical line passing through 3. So 3 is here. So that's left bound, that's right bound. Y is between 0 and 6. Y equal to 0 is here. Y equal to 6. Where is 6? When y is 6, when y equal to 6, if I plug in 6 here, 6 over 2 is 3. So when y equal to 6, x is 3. When y equal to 6, x is 3. So region is between these two curves, between 0 and 6. So set out the integral. Left bound is s equal to y over 2. Right bound is s equal to 3. And y is from 0 to 6. S plus y dx dy. Then let's solve the integral. Do the inner integral first. Take antiderivative with respect to x. We have y from 0 to 6, x squared over 2 plus sy, where x is from y over 2 to 3 dy. Substitute y over 2. Y is from 0 to 6. Substitute y over 2 for each x. If I substitute 3, I have 9 over 2 plus 3y. If I substitute y over 2, I have y over 2 squared over 2, which is y squared over 8. If I substitute y over 2 here for x, I have y squared over 2 dy. Then simplify the function. 9 over 2 plus 3y stays the same. For the second part here, I can combine like term. I get 5y squared over 8 dy. Then take antiderivative. I have 9 over 2y plus 3y squared over 2 minus 5y cubed over 24. Evaluate from 0 to 6. Then I use my calculator. I get 27 plus 54 minus 45 when I plug in 6. I get 0 when I plug in 0. Then 27 plus 54 minus 45 is 36. Next example. Find double integral over region R. S squared plus 2y is the function dA, where R is the region bounded by y equal to x, y equal to 2x, and s equal to 2. So first of all, draw region R first. R is a region bounded by y equal to x, y equal to 2x, and s equal to 2. Draw the region first. Y equal to x is this line. Y equal to 2x is this line. Slope 2. Y-intercept 0, slope 2. S equal to 2 is a vertical line that passing through 2. Vertical line pass through 2. S equal to 2 is a vertical line that passes through 2. That's the region. That's the region. That's region R, bounded by these 3 lines. That's region R, bounded by these 3 lines. Now, for region R, we have 2 choices. We can integrate from left to right, and we can integrate from bottom to top. If we integrate from left to right, we see that here, in different regions, we have different left side and right side curve. In this region here, my left side curve is this line. My right side curve is this line. In this region, my left side curve is this line. My right side curve is this line. So if in different region, we have different left side and right side curve. If we want to integrate from left to right, we must cut into 2 regions. R1 plus R2. But that's too much work. That's too much work. If we integrate from bottom to top, then we can clearly tell this is lower curve, this is upper curve. So integrate from bottom to top will be easier in this problem. If we integrate from bottom to top, it will be easier. So let's integrate from bottom to top. If we integrate from bottom to top, we need to write y in terms of x. We need to write y in terms of x. Lower curve is y equal to x. Upper curve is y equal to 2x. Integrate from bottom to top. Y is from x to 2x. Then x is from, for this region R, x is from 0 to 2. It starts from this point, ends at 2. X is from 0 to 2. S squared plus 2y dA. dA here is dy dx. Then evaluate the inner integral first. Leave an outside the same. Leave an outer integral the same. Take antiderivative with respect to y. We have x squared y plus y squared. Take antiderivative with respect to y. Y is from x to 2x. Leave the x the same. Then we substitute 2x and x for each y. If I substitute 2x, I have 2x to the power 3. If I substitute 2x here, I have 4x squared. If I substitute y equal to x, I have s cubed. If I substitute x, I get s squared. Then combine like terms. Combine like terms. We have s cubed minus 3x squared plus 3x squared, s cubed plus 3x squared dx. Take antiderivative. We have x to the power 4 over 4 plus s cubed. Evaluate from 0 to 2. If I plug in 2 to the power 4 is 16. 16 over 4 is 4. Substitute 2 here. 2 to the power 3 is 8. If I substitute 0, I get 0, which is the answer is 12. Next. Evaluate the double integral over region R. X times e to the power y dA, where R is the region. Bounded by y equal to 4 minus x, y equal to 0, s equal to 0. So first step, no matter how, draw region R first. Y equal to 4 minus x. Y-intercept is 4. Slope is negative 1. Y equal to 0 is the s-axis. S equal to 0 is the y-axis. So next region R. To find this point here, I substitute 0. I substitute 0 for x. I substitute 0 for y. Substitute 0 for y. Solve for x. X is 4. So next region R. Now for region R, we have two choices. We can integrate from left to right or bottom to top. If we integrate from left to right, we have s equal to 0, y equal to 4 minus x. If I solve for x, s is 4 minus y. If I integrate from left to right, we have x from 0 to 4 minus y. Then the lower bound is 0, upper bound is 4. Y equal to 0, y equal to 4. X e y dx dy. If we integrate from left to right, if we integrate from bottom to top, lower bound is y equal to 0, upper bound is y equal to 4 minus x. So I can do I can integrate y from 0 to 4 minus x. Then left bound is s equal to 0, right bound is s equal to 4. dy dx. Now, either way will give you the same answer. Let me solve this one. You verify the other one by yourself. Answer must be the same. Let me solve this one. Solve the inner integral first. Take antiderivative with respect to y. I get x times e to the power y. Evaluate from 0 to 4 minus x dx. If I substitute 4 minus x for y, I have x e to the power of 4 minus x. If I substitute 0, I get e to the power 0. E to the power 0 is 1, so I have x here. This can be rewrite as then we solve these two terms individually. I can separate this into two integrals. Solve each integral individually. For the first integral, we can use integration by parts. Integration by parts. The u be x, the dv be e raised to 4 minus x. Then du will be dx. V will be negative e raised to 4 minus x. Then use the formula u times v minus v times du. I have negative x e raised to 4 minus x from 0 to 4 minus v times du. Double negative is positive. E raised to 4 minus x dx. Then take and leave the last one the same. Last one is x squared over 2. Evaluate from 0 to 4. Then take antiderivative here. I have negative e raised to 4 minus x. Evaluate from 0 to 4. Since we have the same bound everywhere, we can write everything together. Negative x e 4 minus x minus e 4 minus x minus x squared over 2. Evaluate from 0 to 4. If I plug in 4, I have 4 minus 4 is 0. E raised to power 0 is 1. 4 minus 4 is 0. E raised to power 0 is 1. If I plug in 4 here, 4 squared is 16. 16 over 2 is 8. If I substitute 0, first term is 0. 4 minus 0 is 4. I have e to the power 4. If I plug in 0 here, last term is 0. So I have e to the power 4 minus 13. And if you solve the other integral, you must get the same answer. You can verify by yourself. If you solve this integral completely, correctly, you should get exactly the same answer. You can verify by yourself. Next, evaluate the double integral of 2sy over region R, where R is the region between curves y equal to 4 minus s squared and y equal to 4 minus x in quadrant 1. So first step, draw region R first. Y equal to 4 minus s squared. That's a parabola open downward. Y-intercept is 4. And we want to draw the graph in quadrant 1. It's a parabola open downward. Y equal to 4 minus x. That's a straight line. Y-intercept is 4. Slope is negative 1. So that's the region between the curves in quadrant 1. That's the region between curves in quadrant 1. What's the s-intercept here? What's the s-intercept here? For s-intercept, we substitute 0 for y. If I substitute 0 for y for this parabola, solve the equation for x, s is 2. For this straight line, if I substitute 0 for y, solve for x, s is 4. Now, for region R, we can integrate from left to right or from bottom to top. If we integrate from bottom to top, in this region here, the parabola is a lower curve, straight line is upper curve. In this region here, y equal to 0 is a lower curve, and the straight line is upper curve. Since in different regions we have different upper and lower curve, if we integrate from bottom to top, we need to take two integrals. We need to divide R into two regions and take two integrals. It may be too complicated. Easier way, in this problem, if we try to integrate from left to right, then we can see that everywhere we can clearly tell this is the left side curve, this is the right side curve. So integrate from left to right will be much easier for this problem. Integrate from left to right will be much easier. If we integrate the integral from left to right, it will be much easier than from bottom to top. So let's integrate from left to right. Let's integrate from left to right. Let's integrate from left to right. If we integrate from left to right, we must write x in terms of y. So for the parabola, if I write x in terms of y, I have s squared equal to 4 minus y, s equal to square root of 4 minus y. If I write x in terms of y, left side curve is x equal to square root of 4 minus y. Right side curve, if I get s by itself, x is 4 minus y. So that's my left side curve, that's my right side curve. So x from square root of 4 minus y to 4 minus y. How about a boundary for y? What's the boundary for y? What's the boundary for y? If you can see it clearly, push the entire graph into y-axis. Find the projection in the y-axis. Push the entire graph into y-axis. Find the projection in the y-axis. If you push the entire graph into the y-axis, we can see that this line here goes to 0. This point stays at 4. So both curves goes to the region between 0 and 4. So if I push everything into y-axis, I have a line segment from 0 to 4. If I push the entire graph into the y-axis, I have a line segment from 0 to 4. So y is from 0 to 4. So here we can tell y is from 0 to 4. If I push the entire region R into the y-axis, I can see the projection in the y-axis is from 0 to 4. This line goes to 0. Number 4 stays at 4 here. And the region between 0 and 4, both lines go to the region between 0 and 4. That's the projection in the y-axis. So y is from 0 to 4. And the function is 2sy. We have dx, dy. Now do the inner integral first. Take antiderivative with respect to x. Take the antiderivative with respect to x. I have x squared y, x squared y, yes. X is from square root of 4 minus y to 4 minus y. If I plug in the upper limit for x, I have 4 minus y squared times y. If I plug in the lower limit for x, I have 4 minus y squared. Square cancel square root. I get y here. dy. Then this expand perfect square. I have 16 minus ay plus y squared multiplied by y. I get 16y minus ay squared plus y cubed. This should be y minus 4y plus y squared dy. Then combine like terms. Y is from 0 to 4. Y cubed. Let me put it in descending order. Y cubed minus 7y squared plus 12y. dy. Then take antiderivative. We have y to the power 4 over 4 minus 7y cubed over 3 plus 12y squared over 2 is 6y squared. Evaluate from 0 to 4. I use my calculator. I get 256 minus 448 over 3 minus plus 96 when I plug in 4. When I plug in 0, I get 0. Then adding up, I have 608 over 3 as my final answer. Next example. Evaluate the double integral y over 1 plus s squared over region R, where R is the region bounded by y equal to 0, y equal to square root of x, and s equal to 4. So sketch the region first. sketch region R first. Y equal to 0 is the x-axis. Y equal to square root of x. Looks like this. S equal to 4 is a vertical line that goes through 4. That's region R. Lower curve is y equal to 0. Upper curve is y equal to square root of x. So if I can integrate from bottom to top. If I integrate from bottom to top, y is from 0 to square root of x. Then how about my x? How about the boundary? How about my x boundary? To find my s bound, I push the entire graph down to s-axis. If I push the entire graph down to s-axis, the projection in the s-axis is a line segment from 0 to 4. If I push the entire graph down to the s-axis, I have a line segment from 0 to 4. So the boundary for x is from 0 to 4. Then y over 1 plus x squared dy dx. If I integrate from left to right, if I try to integrate from left to right, this is my left side curve. This is my right side curve. This is my left side curve. This is my right side curve. If I integrate from left to right, I write x in terms of y. So y equal to square root of x can be rewritten as s equal to y squared. That's my left side curve. My right side curve is the line s equal to 4. So x is from y squared to 4. X from y squared to 4. Then what's my y bound? In order to find my y bound, I push the entire graph into the y-axis. This entire line goes to 0. This point go to y-axis. And what's this point? What's the y coordinate here? In order to find a y coordinate, I plug in 4 for x. If I substitute 4 for x, square root of 4 is 2, y is 2. So this point goes to 2. And the entire line segment, if I push it into y-axis, the entire line segment go between 0 and 2. And this curve also go between 0 and 2. So that's the projection in the y-axis. This is the projection of this graph in y-axis. So here, y is from 0 to 2. Y over 1 plus x squared dx dy. Either way will give you the same answer. Let me solve it using the first integral. Let me solve the first integral. Either one will give you the same answer. Let me solve the first integral. If I take antiderivative with respect to y, I have y squared over 2 times 1 over 1 plus x squared. Evaluate y from 0 to square root of x. Dx stays the same. Then if I substitute square root of x for y, square cancel square root, I have x over 2 times 1 over 1 plus x squared. If I substitute 0, I get 0. Then here I can use u substitution. let u be 1 plus x squared, and du will be 2x dx. Half of du will be x dx. So there's an extra half here. Pull out this half and this half. We have 1 over 4. Integral of 1 over u du. If I substitute 4 here, I get 17. If I substitute 0, I get 1. Take antiderivative. I have ln of u. Evaluate from 1 to 17. So I have ln of 1 over 4 times ln of 17. If I plug in 1, I get 0. ln of 1 is 0. So the final answer is 1 over 4 ln of 17. Next, integral from 0 to pi, from x to pi, sine y over y, dy dx. So we can solve the inner integral first. How do we solve this integral? If sub doesn't work, integration by parts won't work, tree sub won't work. The only thing I think works is Taylor's theory. The only thing it works, I think, is Taylor's theory. You can write sine as a Taylor theory, then take the theory, take each term, divide by y, then take an antiderivative. But it's doable, but it's too complicated. Is there an easier way? Is there an easier way? If it cannot be done, another option is we try to reverse an order for x and y. If the integral cannot be done, I try to reverse an order for x and y. It may be a little easier. If this integral cannot be done, we can try to reverse an order for x and y. How do we reverse an order for x and y? Let's draw the region first. Let's draw the region R first. So the inner integral here says y is from x to pi. That means this is a lower curve, this is an upper curve, this is a lower curve, this is upper curve. The region R is between these two curves. So let me draw a sketch the graph for this region. Lower bound y equal to x is this line. Y equal to pi is a horizontal line that goes through pi in the y-axis. Y equal to pi is a horizontal line that goes through pi in the y-axis. And we are looking for a region between these two curves. R is a region between these two curves. And x is from 0 to pi. X is from 0 to pi. This curve is y equal to x. When y is pi, x is also pi. So x is from 0 to pi. That's the region between the curves. Now, for this curve, for this integral, we evaluate from top to bottom. If we try to reverse an order, we need to take integral from left to right. This integral originally is from bottom to top, from y equal to x to y equal to pi. It's from bottom to top. If we want to reverse an order, we must integrate from left to right. So integrate from left to right. Left side curve is this line. This line is s equal to 0. Right side curve is this line. If I write x in terms of y, I can write x equal to y. If I write x in terms of y, I write x equal to y. So left side curve is s equal to 0. Right side curve is s equal to y. Then how about y? What's the boundary for y? For y bound, we push the entire region into the y-axis. Find a projection in the y-axis. We try to find a projection in the y-axis. I push the entire graph into y-axis. if I push the entire graph into the y-axis, I get this line segment. Line segment from 0 to pi. So y is from 0 to pi. Then the function stays the same. Sine y over y. X as inner integral. So I must write x here, write y outside. Then evaluate the inner integral first. When I taking antiderivative with respect to y, when I'm taking antiderivative with respect to x, I treat y as constant. So I have sine y over y times x. When I'm taking antiderivative with respect to x, I treat y as constant, so I get sine y over y times x. X is from 0 to y. If I substitute y, for x, I have sine y over y times y, which is sine y. If I substitute 0, I get 0. Then take antiderivative. I have negative cosine y from 0 to pi. Cosine of pi is negative 1. Cosine 0 is 0. Cosine 0 is 1, which is positive 2. So if the integral cannot be done directly, another choice is try to reverse an order. Another option is try to reverse an order. If the integral cannot be done, another choice is try to reverse an order. Next example. Integral from 0 to 2, from x to 2, 2y squared sine sy dy over dx. If we try to take integral for y, it looks okay. We need to take integration by part twice. If we try to take antiderivative with respect to y, that's a polynomial of degree 2 times the trig function times sine function. We must take integration by part twice. Taking integration by parts twice may be too much complicated. Let's try to reverse an order, see if it's doable. It will be better. Let's try to reverse an order, see if it will be better or not. So the inner integral is dy. So lower bound is y equal to x. Upper bound is y equal to 2. If I sketch the graph, this will be the lower curve. This will be my upper curve. Y equal to x will be my lower curve. Y equal to 2 will be upper curve. Y equal to x is this line. Y equal to 2 is this line. Horizontal line going through 2. That's the region between two curves, between y equal to x and y equal to 2. X is from 0 to 2. Then, since for this original integral, we integrate from bottom to top, from x to 2, we integrate from bottom to top. If we try to reverse an order, we need to integrate from left to right. If we try to reverse order, we need to integrate from left to right. So let's integrate from left to right. Left side curve is s equal to 0. Right side curve is s equal to y. If I write s in terms of y, I have s equal to y. So this integral, if I reverse an order, it can be rewritten as x from 0 to y. That's left side, left bound. That's right bound. S from 0 to y. Then for the y bound, we push the entire graph into the y-axis. We find a projection in the y-axis. Here, projection in the y-axis is a line segment from 0 to 2. Y is from 0 to 2. The function stays the same. Sin sy dx dy. Does it look a little better? Let's try. If I take antiderivative with respect to x, I have 2y squared times 1 over y times negative cosine sy. If I take antiderivative with respect to x, evaluate from 0 to y. dy. Simplify. I have negative 2y cosine sy. Evaluate from s equal to 0 to s equal to y. If I plug in y, I have cosine y squared if I plug in y for x, I have cosine y squared. If I substitute 0, cosine 0 is 1. If I substitute 0 here, cosine 0 is 1. This can be rewrite as I can pull out 2y. If I pull out 2y, I have negative cosine y squared plus 1. That's not necessary. Leave it the way it is. Negative 2y cosine y squared plus 2y. Take antiderivative with respect to y. Here we need a u substitution. If I let u be y squared, my du will be 2y dy. So this will be my du. Then take antiderivative. This integral can be rewrite as negative cosine of u du. If I take antiderivative, I have negative sine u plus c, and u is y squared. So take antiderivative, I have negative sine y squared plus y squared. Evaluate from 0 to 2. If I substitute 2, I get negative sine 4 plus 4. If I substitute 0, I get 0. So the answer is 4 minus sine 4. Next example. Outer integral from 0 to 1. Inner integral from y to 1. S squared times e to the power of sy dx dy. If we try to solve this integral directly, we must do the inner integral first. For the inner integral, we are taking antiderivative with respect to x. In this problem, we must do integration by parts twice. It may be too much work. So a better choice is we can try to reverse the order for x and y. It may be a little easier. So when we try to reverse the order for x and y, let's draw region R first. Let's look at the inner integral. Lower bound is x equal to y. Upper bound is s equal to 1. So the lower bound here is the left side curve. Upper bound is the right side curve. So left side curve is s equal to y, which is the same as y equal to x. That's the left side curve. Right side curve is s equal to 1. That's a vertical line going through 1 in the x-axis. So this is a left side curve. This is a right side curve. This curve is y equal to x. This curve is s equal to 1. When s equal to 1, y is also 1. So this point here is 1 on the y-axis. This point is 1 on the y-axis. This is a left side curve. This is a right side curve. Y varies from 0 to 1. So that's a region between two curves. That's a region between two curves. This is region R. This is region R. We're taking integral over this region R. Now, since we try to reverse order for x and y, here we try to switch order. We try to integrate from bottom to top. Instead of from left to right, we take integral from bottom to top. So the lower curve is y equal to 0. It's an s-axis. S-axis is y equal to 0. Upper curve is y equal to x. So lower curve is y equal to 0. Upper curve is y equal to x. And for the x value, we try to find a projection in the s-axis. If I push entire region R into the s-axis, if I push the entire region R down to s-axis, I have a line segment from 0 to 1. If I push region R down to s-axis, this point stays at 0. This point goes to 1. I have a line segment from 0 to 1. So x varies from 0 to 1. Integrand stays the same. S squared e to the power of sy dy dx. And then let's solve it. Let's solve this integral. We take the inner integral first. For the inner integral, take antiderivative with respect to y. So we keep an outer integral the same. Take antiderivative with respect to y. I have x squared times 1 over x times e to the power of sy. Take antiderivative with respect to y. I get 1 over x times e to the power of sy. I treat s squared as a constant. It stays the same. Y is from 0 to x dx. Then this integral can be simplified as x times e to the power of sy. Y is from 0 to x dx. Then substitute upper and lower limit and take the difference. X is from 0 to 1. If I substitute x for y, I get x times e to the power of s squared. If I substitute 0 for y, I get x times e to the power of 0. E to the power of 0 is 1 dx. This integral can be rewritten as x times e to the power of s squared minus 1 dx. Here we can make u substitution. Let u be x squared, then du will be 2x dx. So this integral can be rewritten as e to the power of u minus 1 times half of du. X times dx is half of du. And for the limits, if I plug in 1 for x, 1 squared is 1. If I plug in 0 for x, 0 squared is 0. Half is a constant, I can put it outside. Then take antiderivative for e to the power of u, I get e to the power of u. If I take antiderivative for 1, I get u. Evaluate from 0 to 1. If I plug in 1, e to the power of 1 is e. If I plug in 1, u itself, u is 1. If I plug in 0, e to the power of 0 is 1. If I plug in 0 for u, I get 0. Which is half of e minus half minus half. Negative half and negative half together is 1. So the final answer is half of e minus 1. Next example. Outer integral is from 0 to 3. Inner integral is from radical s over 3 to 1. E to the power of y cubed dy dx. If we try to solve this integral directly, we must do the inner integral first. But for the inner integral, we must take antiderivative of e to the power of y cubed with respect to y, which is very hard. A better choice is we can try to reverse order for x and y. It may be a little easier. In order to switch order for x and y, let's draw the region R first. So lower bound is y equal to radical s over 3. Upper bound is y equal to 1. So that's the lower curve. That's an upper curve. Let's draw both curves first. Lower curve, y equal to radical s over 3. It's a parabola. Y equal to radical s over 3. That's a lower curve. Upper curve is y equal to 1. That's a horizontal line going through 1 in the y-axis. That's a horizontal line going through 1 in the y-axis. That's an upper curve. That's a lower curve. And what's the intersection here? For the intersection, y is 1. If I plug in 1 for y, x must be 3. If I plug in 1 for y and solve the equation for x must be 3. 3 over 3 is 1. S must be 3. Then x varies from 0 to 3. X varies from 0 to 3. And the region R is a region between the lower curve and upper curve. So this is region R. This is region R. Now, originally we integrate from bottom to top. That's lower curve, that's upper curve. If we try to reverse the order, we must integrate from left to right. If we try to reverse order, we need to integrate from left to right. So left side curve is this vertical line here. That's s equal to 0. This is the right side curve. This is the right side curve. Y equal to radical x over 3. If we try to integrate from left to right, we must write x in terms of y. If we try to integrate from left to right, we must write x in terms of y. So let's solve this equation for x. Y equal to radical s over 3. If I square both sides, y squared equal to s over 3. If I multiply both sides by 3, 3y squared equal to x. So y equal to square root of s over 3 can be rewritten as s equal to 3y squared. So that's the left side curve. That's the right side curve. Left side curve is s equal to 0. Right side curve is s equal to 3y squared. That's the left side curve. That's the right side curve. Next, for the y bound, we try to find a projection of this region R in the y-axis. For the y bound, we try to find a projection of region R in the y-axis. If I push the entire region R into the y-axis, this point stays at 0. This point goes to 1 in the y-axis. So we have a line segment from 0 to 1 in the y-axis. Projection of region R is this line segment in the y-axis. If I push region R into y-axis, I have a line segment from 0 to 1. So y varies from 0 to 1. Integrand stays the same. E to the power of y cubed dx dy. Next, we solve the integral. Here we start from the inner integral first. For inner integral, I take antiderivative with respect to x. So I treat e to the power of y cubed as a constant. So the antiderivative is e to the power of y cubed times x. X is from 0 to 3y squared dy. Then plug in the upper and lower limit and take difference. If I plug in lower limit, I get 0. So that's nothing. All I need is plug in upper limit. If I plug in upper limit for x, I get 3y squared times e to the power of y cubed. If I plug in upper limit for x, I get 3y squared times e to the power of y cubed dy. If I plug in lower limit, I get 0. Then take antiderivative with respect to y. Here we can try to make a u substitution. Let u equal to y cubed. Then du will be 3y squared dy. So y to the power 3 become u. I get e to the power u here. 3y squared dy become du. And for the upper and lower limit here, if I plug in 1 for y, 1 cube is 1. If I plug in 0 for y, 0 cube is 0. Then take antiderivative with respect to u. I get e to the power u from 0 to 1. If I plug in 1, I get e. If I plug in 0, e to the power 0 is 1. So the answer is e minus 1. That's the answer to this double integral. Next example. Find the area between curves y equal to 5x minus x squared and y equal to x using double integrals. How do we find area between curves using double integrals? Double integral represents volume under the surface. How do we find area using double integrals? Double integral represents volume between surface. So think of this. For any cylindrical surface, the volume is always base area times height. For any cylindrical surface, for any cylindrical solid, its volume is always base area times height. What's called cylindrical solid? If the top is horizontal, bottom is also horizontal and they have exactly the same shape. If the bottom has a horizontal surface, bottom also have a horizontal surface and they are exactly the same shape. Also, all curves on the side, all edges on the side are vertical. That's called cylindrical surface. The top and the bottom have exactly the same shape, and both top and the bottom has horizontal surface, and the edges on the side, all edges on the side are vertical. All edges on the side are vertical. That's called cylindrical solid. So for the volume of a cylindrical solid, we take the base area times the height. Take base area times the height. That's the volume of a cylindrical solid. Now, if in a special case, if the height is 1, for a cylindrical solid, if its height is 1, for a cylindrical solid, if its height is 1, then the volume equal base area times 1. The volume equal to base area times 1, which means the volume and the base area have the same value. Of course, they have different units, but the volume and base area have the same numerical value. If the height of a cylindrical solid is 1, then the volume and the base area have exactly the same value, same numerical value. Now, consider this surface, g equal to 1. If we try to find the volume under the surface, over region R, how it looks like? suppose that's R. Suppose that's region R. Then Z equal to 1 is the same shape of solid. Z equal to 1 is a plane. Z equal to 1 is a plane parallel to SY plane and passing through 1 in Z axis. So that's the region, that's the volume under the surface. That's the region under the surface. The top surface is Z equal to 1. The top surface is Z equal to 1. Bottom surface is the SY plane. SY plane is Z equal to 0. And the height here, we can see that the height from 0 to 1 is 1. Z equal to 0, Z equal to 1, they are both horizontal planes. This is a cylindrical solid. This is a cylindrical solid. Its volume is base area times height. But here the height is 1. When the height is 1, the volume and the base area have exactly the same numerical value. When the height is 1, the base area and the volume have the same numerical value. So this equal to the area of R. The base is region R. So this is region, this double integral equal to the area of R. The value is the same. The numerical value is the same. This double integral represents the area of region R. So keep it in mind. This integral represents area of region R. So if we try to find the area between curves using double integrals, we use the formula. Double integral over region R. Double integral of 1 over region R, dA. And here region R is the region between these two curves. R is a region between these two curves. Let's draw region R here. Let's draw region R. So keep it in mind that area of region R is always the double integral of 1 over region R, dA. Now let's draw the region first. Y equal to 0 is this line. So y equal to x is this line. Y equal to 5x minus y equal to 5x minus x squared. That's a parabola open downward. That's a parabola open downward. The s-intercept is 0 and 5. That's a parabola open downward. S-intercept is 0 and 5. That's a parabola open downward. S-intercept is 0 and 5. And R is the region between these two curves. This is region R. R is the region between these two curves. So for this region R, it's better to integrate from bottom to top. If we integrate from left to right, for this region, we must cut the parabola into two pieces. Then find the left side curve and right side curve. That's very complicated. So easier way is we integrate from bottom to top. That'll be much easier. Lower curve is y equal to x. If we integrate from bottom to top, write y in terms of x. If we integrate from bottom to top, write y in terms of x. Lower curve is y equal to x. Upper curve, the parabola is 5x minus x squared. So lower bound is y equal to x. Upper bound is 5x minus x squared. What's the s-bound? What's the s-bound? If I push the entire graph down to s-axis, this point stays as 1. The entire region will go into this line segment here. The entire region will go into this line segment here. But we don't know this point here. How do we find this point? This point is the intersection of these two curves. This point is the intersection of these two curves. So I said they are equal to each other. I set phi x minus s squared equal to x. Solve the equation for x. I have 4x minus x squared equal to 0. If I factor s out, I get x times 4 minus s equal to 0. Solve the equation, either s equal to 0 or 4 equal to x. So either s equal to 0 or s equal to 4. S equal to 0 is here, one of the intersection. S equal to 4, that's another intersection. So if I push the entire region down to the s-axis, the projection is this line segment from 0 to 4. So take x from 0 to 4. 1 times dy dx. Then take inner integral. X is from 0 to 4. Take inner integral. Antiderivative of 1 with respect to y, it will be y. Y from x to phi x minus x squared dx. Substitute. If I substitute phi x minus x squared, I get phi x minus x squared. If I substitute x, I get x. Then simplify. I have 4x minus x squared dx. Take antiderivative. I have 2x squared minus s cubed over 3. Evaluate from 0 to 4. If I substitute 4, I get 32 minus 64 over 3. Common denominator is 3. 36 times 3 is 96. 96 minus 64 is 32 over 3. That's the area between the two curves. So for area of region R, it's always double integral of 1 over region R. Next example, find the area of the region between curves s equal to y squared minus 4y and s equal to 2y minus y squared using double integrals. So if we try to use double integral to find the area, the formula is double integral of number 1 over region R dA. Let's first of all draw the region first. Draw region R first. S equal to y squared minus 4y. That's a parabola. And y-intercept is 0 and 4. Hence y squared is positive. It's open to the right. Open to the right. Y equal to 2 minus s squared. That's also a parabola. Y-intercept is 0 and 2. Since y squared is negative, it opens to the left. So that's the region between two curves. That's the region between two curves. So for this region, you can clearly see that if we integrate from left to right, it will be much easier. If we integrate from left to right, it will be much easier. So left side curve is s equal to y squared minus 4y. Right side curve is s equal to 2y minus y squared. Integrate from left to right. S equal to y squared minus 4y. The upper bound is s equal to 2y minus y squared. That's left bound, that's right bound. That's left bound, and that's right bound. Now what's the boundary for y? In order to find a boundary for y, we try to push the entire graph into the y-axis. Push the entire graph in both directions. Push the the entire graph into the y-axis. Find the projection in the y-axis. So you can see that 0 stays at 0. This region go to y-axis. This region also go to y-axis until this point here. What's this point? In order to find this point, I set the function equal to each other. Set y squared minus 4y equal to 2y minus y squared. If I solve an equation for y squared, I have 2y squared minus 6y equal to 0. I can factor, pull out 2y, I get y minus 3. Set equal to 0, y equal to 0, y equal to 3. So 0 is here, this point must be 3. Which means if I push the entire graph into the y-axis, the projection is a line segment from 0 to 3. If I push everything into the y-axis, the projection is a line segment from 0 to 3. 1 times dx dy. Then take antiderivative with respect to x. Antiderivative of 1 with respect to x is x. X from y squared minus 4y to 2y minus y squared dy. Substitute 2y minus y squared. And substitute y squared minus 4y. Combine like terms. I have 6y minus 2y squared dy. Then take antiderivative. I have 3y squared minus 2y cubed over 3. Evaluate from 0 to 3. If I plug in 3 squared is 9. 9 times 3 is 27. 3 cubed is 27. 27 over 3 is 9. 9 times 2 is 18. When I plug in 0, I get 0. 27 minus 18 is 9. That's an area between these two curves. Number 15. Find the volume of the solid bounded by the plane 3x plus 2y plus z equal to 6 and the coordinate planes. Find the volume of the solid bounded by the plane and the coordinate plane. Let's draw the picture first. Usually we can use double integral to find the volume, but let's draw the picture first. Otherwise we can't set it up. Let's draw the picture first. This is a plane. If I try to find the s coordinate, if I try to find s-intercept, I set y equals 0, z equals 0, s equals to 2. If I try to find a y-intercept, I set s equals 0, z equals 0, so y equals to 3. If I try to find the z coordinate, z-intercepts, I set s equals 0, y equals 0, so z equals to 6. Three point can fix a plane. If I know 3 points in a plane, I can draw the plane. So this is the plane. The coordinate planes is the SY plane, XZ plane, and YZ plane. this is the solid. This is the solid we try to find. This is the solid which we try to compute the volume. So here we can see that G equal, we are looking for the volume below the surface of this plane. This plane can be rewritten as G equal to 6 minus 3x minus 2y. This plane can be rewritten as G equal to 6 minus 3x minus 2y. So we are looking for the volume under this surface. We are looking for the volume under this surface. And what's region R? The region R is here in the xy plane. That's region R in the xy plane. If I draw region R here on the side, region R is this triangle in the xy plane, which goes through 2 in the x-axis and goes through 3 in the y-axis. This is region R. This is region R in xy plane. So we are looking for the volume under this surface over region R. We are looking for the volume under the surface over region R. That's the solid bounded by this plane and the coordinate planes. The solid bounded by this plane and the coordinate plane is the solid under this plane over region R. So we are looking for the volume here is double integral over region R. The function is 6, the surface is 6 minus 3x minus 2y dA. Now let's set up a double integral. For region R, we can integrate from left to right or bottom to top. Either way is okay. Let me integrate from bottom to top. Lower curve is y equal to 0. Upper curve is a line. We can use the equation y equal ms b to find the line. Y equal ms plus b to find the line. We know that for this line, the y-intercept is 3. So b is 3. What's the slope? Slope is rise over long, 3 over 2. But the line is going down, so it's negative 3 over 2. That's this line. That's the equation of the line. So the lower bound is y equal to 0. Lower curve is y equal to 0. Upper curve is y equal to negative 3 over 2x plus 3. Y equal to 0, y equal to negative 3 over 2x plus 3. How do we find a bound for x? If I push the entire graph down to s-axis, if I try to find a projection in the s-axis, this point goes to 0. This entire line segment goes to the region between 0 and 2. So if I push everything down to s-axis, I have a line segment from 0 to 2. So x is from 0 to 2. 6 minus 3x minus 2y dy dx. Then take antiderivative with respect to y. I have 6y minus 3sy minus y squared. Evaluate y from 0 to negative 3 over 2x plus 3 dx. Then substitute the upper bound and lower bound. Six times negative 3 over 2x plus 3 minus 3x times negative 3 over 2x plus 3 minus negative 3 over 2x plus 3 squared dx. Then simplify. I have negative 9x plus 18 plus 9x over 2 minus 9 minus 9x positive 9x squared over 2 minus 9x minus 9 over 4 x squared plus 9x minus 9 dx. Then combine like terms. I have 9 over 4 x squared. Negative 9x, positive 9x can cancel. We have negative 9x left. 18 minus 9 is positive 9. Then take an antiderivative. Take an antiderivative. I get 9 over 4 over s cubed over 3 minus 9x squared over 2 plus 9x. Evaluate from 0 to 2. If I plug in 2, 2 cubed is 8. 8 divided by 4 is 2. 9 divided by 3 is 3. 3 times 2 is 6. If I substitute 2 here, 2 squared is 4. 4 over 2 is 2. 2 times 9 is 18. 2 times 9 is 18. When I substitute 0, I get 0, which is 6. So the 6 is the volume. 6 is the volume below the plane and bounded by the coordinate plane. 6 is the volume of the solid bounded by this plane and the coordinate plane. Number 16. Find the volume of the solid bounded by the surfaces z equal to s squared, y equal to s squared, z equal to 0, and y equal to 4. So in order to find the solid bounded by the surfaces, let's draw the surfaces first. Z equal to s squared, that's a cylindrical surface. Because y is missing, that's a cylindrical surface. It's a parabola open upward. That's the surface. Z equal to s squared. Y equal to s squared. It's also here. Z is missing. It's also a cylindrical surface. That's the surface. Y equal to x squared. Z equal to 0 is an SY plane. Y equal to 4 is a plane. Y equal to 4 is a plane parallel to XZ plane and passing through 4 in the y-axis. Let's combine this graph together. Y equal to s squared. In the SY plane, the graph is a parabola. It's bounded by y equal to 4. That's the parabola in the SY plane. Then when y equal to 4, s equal to positive negative 2. When y equal to 4, s equal to positive negative 2. When s equal to positive negative 2, z is also 4. and that's the intersection between these two cylindrical. That's the intersection between these two cylindrical surfaces. So we can see that here we are looking for the solid. We are looking for the solid below the surface. We are looking for the solid below the surface. Below the surface, g equal to x squared. We are looking for the solid below the surface, g equal to x squared. Then the region R, if you look at the picture from top to bottom, region R, to find the region R, you try to push the entire graph down to xy plane. In order to see region R, push the entire graph down to xy plane. Then you can see region R. We're looking for the region below the surface, g equal to x squared. We're looking for the region below the surface, g equal to x squared. In order to see region R in xy plane, we push the entire graph into the xy plane. That's called a projection in the xy plane. So here we can see that this is region R. This parabola is on region R. It's bounded by the line y equal to 4. And the x coordinate is negative 2 and positive 2. This is region R. This is region R. If you look at the picture from top to bottom, you can see that this is region R. You push the entire graph down to xy plane. Push the entire graph down to xy plane. This is the projection of this solid. Then let's set it up. Since we are looking for the volume below the surface, let's double integral of R s squared dA. We are looking for the volume below the surface, g equal to s squared. G equal to s squared, that's the volume, that's the surface above everything. So we are looking for the volume below this surface. How do we set out the integral? Here, let's try to integrate from bottom to top. Lower curve is this parabola. This parabola is y equal to s squared. Upper curve is y equal to 4. So integrate from bottom to top. Y from x squared to 4. X, what's s coordinate? What's s bound? If you push region R into s-axis, if we push region R into s-axis, the projection is a line segment from negative 2 to 2. If we push region R into s-axis, the projection is a line segment from negative 2 to 2. So x is from negative 2 to 2. S squared dy dx. Then solve the integral from outer to inner. Sorry, from inner to outer. X from negative 2 to 2. Take antiderivative with respect to y. We have s squared y. Y is from x squared to 4. dx. If I substitute 4 for y, I have 4x squared. If I substitute x squared for y, we have x to the power 4. Take antiderivative. We have 4x cubed over 3 minus x to the power 5 over 5 from negative 2 to 2. if I substitute 2, 2 to the power 3 is 8. 8 times 4 is 32. I get 32 over 3. If I substitute 2, 2 to the power 5 is 32. I get 32 over 5. If I substitute negative 2, I get negative 32 over 3. Substitute negative 2, I get positive 32 over 5. Combine like terms, let's add these two terms first. I get 64 over 3 minus 64 over 5. Then I use my calculator. I get 15 on the bottom, 128 on the top. So the volume of this solid bounded by these four surfaces is 128 over 15. So in general, when we try to find the volume of a solid, draw the 3D graph first, then find out what's the upper surface, what's the region in xy plane, then take the integral. Next, I will show you something about property of double integrals. First property, assuming all the following integral exists. The first property, double integral of f of xy plus g of sy over any region R is the same as double integral of f of sy over region R plus the double integral of g of sy over region R. Assume all the following integral exists. Next, double integral of a constant times the function of sy over region R. I can always pull out the constant. C times double integral f of sy dA. Next, if S and T are disjoint subsets of R, if S and T are disjoint subsets of R, and S union T equal to R, then double integral of R then double integral of R f of sy dA is equal to double integral of S f of sy dA plus double integral of T, double integral of f of sy over T. What does it mean? Why is this true? Let me show you a picture, it will make more sense to you. Why is this true? So R is a set, R is a region in R2. R is a region in R2. S and T, they are subsets of R. S and T, they are subsets of R. They are disjoint subsets of R. Disjoint subset means they have nothing in common. Disjoint subset means they have nothing in common. They are disjoint subsets of R. And S union T is R. That means if I add S and T, if I combine S and T together, I get R. So double integral of f of sy over R. That means we are looking for the surface area of f. We are looking for the surface area of g equal to f of sy. We are looking for the surface area. Sorry, we are looking for the volume under the surface. We are looking for the volume under this surface over region R. F of sy, double integral of f of sy over s. That means the volume under the surface over region S. This part means volume under the surface f of sy over region T. The volume below the surface over region R must be the same as the volume below the surface over region S plus the volume under the surface over region T. Therefore, they are the same. Next property, if f of sy is greater than or equal to g of sy for all points sy in R, then the double integral f of sy over region R is greater than or equal to the double integral of g of sy over region R. The reason is because when f is greater than g for all sy in R, that means the surface of f is above the surface of g. And remember, double integral represents volume under the surface. If the surface of f is above the surface of g, then of course there are more volume under the surface. That's why double integral of f is greater than double integral of g over the same region R. Next, if f of sy is between small m and big M for all sy in R, this means the function f is bounded by these two numbers. Function f is bounded by these two numbers, bounded by small f and big M. Then the double integral of f of sy over region R is bounded by M times area of region R and big M times area of region R, where A of R represents the area of region R. If f is between small m and big M, then the double integral of f of sy over region R is bounded by small m times the area and big M times the area of region R. The reason this is true is because if f is between small m and big M, we treat this small m as constant functions. Let g of sy equal to m. Let h of sy equal to big M. Then we know that we have f of sy is less than g of sy is less than h of sy. By property number 4, by the previous property, we know that the double integral of g of sy over region R is less than the double integral of f of sy over region R is less than the double integral h of sy over region R. And we know that g of sy is small m. h of sy is big M. M is a constant. I can pull it outside the integral by property number 2. I can pull out constant. I can pull constant outside the integral. M is a constant. I can pull it outside. If I pull out M, I have double integral of 1 times dA. The middle stays the same. On the right side, I can pull out big M. Big M is also constant. I can pull out big M. Then double integral of number 1 over region R. This is the area of region R. And double integral of number 1 over region R. This is area of region R. That's why. Double integral of f of sy over region R is between small m times area of region R and big M times area of region R. That's property number 5. Keep this property in mind. You will need to use it for your future class.